John Kessler is our speaker today. John has an interesting background. After he did his undergraduate, he worked for a few years in an atmospheric chemistry group at NIST. So he's somebody who's actually crossed the boundary into atmospheric sciences as well as marine sciences. Then he went to the UC Irvine, where he worked with Bill Rehberg on methane. And I believe you were Bill's last student, right?
He kind of had one more in Mary Pack. That kind of finished up as he was transitioning out.
Yeah, so, but one of the last students.
Correct.
And he's like Mr. Methane. And John then did a postdoc at Princeton, and he's going to, I think you're going to talk some about the new techniques that are you going to talk about your new techniques at all or not? Anyway, he has some very innovative ways of measuring stable isotopes in methane, and so people should feel free to talk to him after or at the lunch about that. And then now he's at the university. Then he went from there to Texas A&M, where he was very involved with the Deep Horizon oil spill and the monitoring of methane after that, and became an expert at speaking on National Public Radio and television. I saw his face as much as almost anybody else that I knew from the scientific community. And I think your public speaking really improved dramatically. And not that it was bad to start with, but you got lots of experience. And now he's at the University of Rochester, where he is continuing his work on isotopes.
Yeah. Thank you. Thank you. Nothing of what, there was a few humorous points in there. Nothing of what Mary said is untrue. All of that is true, and I think even in what she implies maybe is I was a little less seasoned at the beginning of the oil spill. It's incredibly true. There's so much I would do differently, would say differently, what I said maybe at the beginning with how I would act now if the exact same situation was to occur today.
So for those people interested in scientific communication, John is a good person to say.
Well, trial by fire. It's probably, I think AGU runs a few seminars on how to do it appropriately. And I highly recommend those rather than kind of going through the missteps that I did on public television and everything else. Anyway, our work that we did in the oil spill actually comes into play a little bit in the talk that I wanted to go over today. But in general, what I would like to describe is how we can use stable isotopes to determine the ultimate fate of a perturbation, a chemical perturbation in this sense. As Mary stated, I'm very much interested in studying the oceanic methane system and the dynamics of that methane system. And the reason why I'm interested in it is twofold. Number one, it is one of the largest global carbon reservoirs on the planet. Methane is a potent greenhouse gas, as well as there's the potential for releases, destabilizations of, let's say, methane hydrates, even some sediment methane, due to changing ocean temperatures, changing circulation patterns, releasing that methane, possibly to then ultimately dissolve in ocean waters or being released to the atmosphere. And then really what I'm going to be addressing today is the topic of once it's been released. Let's say in this case where I'll be going over more today is once it's dissolved in the waters, how can we use measurements of the stable isotopes to ultimately determine the fate of that released methane, that perturbation? Can we use that to determine how much of that signal has simply been dispersed through larger circulation and mixing patterns versus how much has been actually removed from the system via a biogeochemical reaction, a biodegradation, let's say. Here we have a picture of some work that I've done normally outside of the oil spill, taken from Coal Oil Point. The lines that we see here are bubble streams of nearly pure methane coming out. And again, this is what we try to investigate. What are the controlling dynamics of this system? What controls the rate at which it's being released or not released? Where is it ending up? What's the ultimate fate of it once it goes there? And so, in a natural sense, we certainly can have large perturbations and then ultimately trying to understand where that goes in time. Probably the most well-documented, or at least discussed, case of a large global methane release from the oceans, methane hydrates, people have investigated the Paleocene-Eocene thermal maximum. And here we just look at some of the stable isotope signatures of various carbonate reservoirs, since this is roughly 55 million years ago. And we see this large perturbation that occurs in these global carbon reservoirs, and then as it starts to relax and go back to its more normal state. But in our more modern existence, we're not talking about time scales of millions of years. We're normally talking about for one of these types of perturbations. And again, what I'm abstractly talking about, I think, can be applied universally to any sort of chemical perturbation. But what I'm going to be following more is the view of oceanic methane, a methane perturbation. And on the time scales that we're normally investigating in a modern context, we're looking at things, a perturbation that might occur in terms of days, weeks, months, on the long time, maybe a year or slightly more. Certainly not in the time scales of thousands, hundreds of thousands, possibly millions of years. For the Deepwater Horizon incident, we saw one of those such events. In total, during that disaster, there was roughly a teragram of total hydrocarbons that were released to the environment. Methane was by far the dominant hydrocarbon that was released. It accounted for about 15% of the mass. So about a tenth, maybe a little bit more of a teragram of methane mass was emitted over 83 days. I tried to scale this a few different ways. In a previous version of this talk, I scaled it to the Kariako Basin, and I'm kicking myself for not bringing that calculation here. But I believe, if I'm remembering correctly, the amount of methane that was released in the 83 days of this disaster was on the order of about 50 years of release in the Kariako Basin. It's equivalent to, in magnitude, to the flux of methane out of the entire Black Sea, but now it's concentrated down into a 20-centimeter diameter pipe. So it was a tremendous amount of methane, the potential to make a very large perturbation, and our goals were to try to understand what the larger term fate of this was. My involvement in this disaster was one that began primarily based on hypothesis-driven science. We could use this disaster as an analog to a natural release, which we study so often. And now, this is by far the largest release that we could have ever studied. We can ultimately use this to determine very simple questions, such as how much went to the atmosphere, how much went to the ocean, and what the longer-term fate of both of those, where it ultimately went, what its longer-term fate was. So the first very thing we tried to do is to try to determine how much went to the atmosphere versus how much stayed in the waters. The very first thing that we wanted to do was measure the air-sea flux. So we used, and this again gets into a little bit of Mary's comments about technology and things that we've developed, a version of one of Ray Weiss's seawater equilibrators. It's basically a shower head and an enclosed cylinder. You're increasing the surface area of the water so you get a very rapid air-water exchange, a rapid equilibration with that headspace. Then you can pump off that headspace and measure dissolved gases. We used a cavity ring-down spectrometer. This one we bought, not one of the ones that we developed in the laboratory. But you can analyze that gas in a non-destructive and very rapid fashion. After we measure it, we then recycle it back into the headspace. So right here, this is actually a map of discrete data points, not a contour of lines of the data, of that sea surface concentration of methane, the partial pressure of dissolved methane in the ocean surface. The star indicates the wellhead, and these are all, you can see the track lines of where our boat went in our first investigation of that disaster back in June of 2010. The scale that we have here, the concentrations that we're seeing in the surface waters are all roughly on the realm of about 2 to 3 parts per million. This is roughly a background concentration that we would normally see that's roughly in equilibrium with the atmosphere. To get the flux coming out of the ocean and into the atmosphere, we have to compare that against the atmospheric concentration. And again, here, the data that we have suggests that this is right around background concentrations. The scale here runs from 2.1 parts per million down to about 1.75 parts per million. Again, roughly equal to what normal background concentrations are in the atmosphere. When we compare that with wind speed, we can pull out the air-sea flux. And again, we're seeing relatively low air-sea fluxes of methane all around the wellhead. This table, I think, says it in its most clear fashion. The average flux that we measured during that first expedition was only about 0.02 micromoles per meter squared per day. When we look at the wind speed that we measured, fortunately, in that first expedition out, it was incredibly calm. We had less than a meter per second for our wind speed. That translates to a flux per day, as we see here, and if we extrapolate that over the entire 83 days of this disaster, we see less than 2,000 moles of methane vented to the atmosphere. If we arbitrarily increase the wind speed to 10 meters per second, we still see a flux of methane that, when we compare it against the total release, is less than 0.01% of the total methane that was released from the well being emitted from the atmosphere. Nothing, as we have documented, went to the atmosphere. So our search for it then extended below the sea surface. And as we lowered our rosette package with normal CTD equipment on it, we have our oxygen profiles here. We have a fluorescence profile over here. These look fairly typical until we get to this depth of roughly 1,000, 1,100 meters. And again, people that have been more active in the spill, I assume there's a few people in the room that have looked at these things, have seen profiles like this before. But the fluorescence profile is mainly looking at dissolved hydrocarbons that are normally attributed to dissolved oil in this context. And we see this spike around 1,100 meters, and concurrent with that, we see a little bit of a sag in the amount of dissolved oxygen, which we're interpreting as being the fingerprint of biodegradation, removing oxygen from the water as it's respiring those oil hydrocarbons. And lo and behold, in that exact same depth range is where we saw all of the methane that was released. Not really much below it, not really much above it, but in these discrete layers is where we see very concentrated plumes of this methane. When we contour out 4 of our stations, we start to see the formation of a primary plume around 1,050 meters depth, a secondary plume about 200 meters higher at about 850, and even occasionally we'd see signs of a tertiary plume about 200 meters high above that, about 650 meters depth, which is not shown in these 4 specific stations. The concentration change that we saw going into and out of those plumes was enormous. 2, 3, 4 orders of magnitude concentration change going above and below it. So the question is this, as I pose it. Can we look at this system and say we can make some rather simple, rather fundamental measurements and determine how much of this concentrated perturbation, this plume, as time progresses, as that concentration drops, can we determine how much has simply been dispersed versus how much has been biodegraded? For methane, it's not as big of a deal. And the government isn't as worried about it. Mainly because methane is not normally looked at as one of the really toxic components that's associated with an oil spill. The VTEX compounds, benzene, toluene, ethylbenzene, and xylenes are really the big ones. They're really interested in these because they want these parameters gone from the system. Dispersion means that yes, maybe they're not as concentrated, but they're still in the system. Biodegradation means that inherently it's gone. So they're very interested in separating out those 2 components. And stable isotopes give us the potential to do just that. In this just kind of thought example, if we look at methane and the 2 different stable isotopes of the C12 species of methane versus the C13 species, these are not drawn to the normal abundances here. The C13 is normally only about 1% as abundant as C12 out in nature. But in general, this is just a schematic. If we look at this as our normal distribution, let's say we've got more or less a 1-to-1 distribution for the amount of C13 relative to C12. If things are going to be dispersed, we're not going to see that ratio change. They're going to still have the same amount of C13 relative to C12. However, if we do have a biodegradation type of signature on here, what is normally observed is there's a preferential degradation for the light isotope relative to the heavy isotope. The rate of reaction of the light isotope is slightly faster than the rate of the reaction for the heavy isotope. So for the residual methane, for the residual hydrocarbon, we actually see an enrichment in the heavy isotope. That light isotope has gone away faster. So that lighter pool we see less of. We see more of that heavy pool. When we look at the ratios between the two, we see that that has changed. We can get some evidence then that there's been a biodegradation type of signature. But we'd like to be a little bit more quantitative about this. We don't want to just say, okay, I've made a couple of stable isotope measurements, biodegradation is happening. We want to be able to go to somebody and say, I can say with full confidence that 80% of this, 90% of this, 20% of this has been biodegraded. And the ways that that's normally done is with something that's referred to as the Rayleigh distillation equations. The Rayleigh distillation equations are simply looking at a chemical reaction. It's looking at this as if it's a first-order chemical reaction. And in a sense, they're looking at it as a closed system. We look at it as if we have a beaker. We take our beaker, we dump our chemical into it, we close that beaker off, so nothing is allowed to escape, we're not adding anything more. And the only way that we can change the concentration of what we just dumped in as our reactant is to react it away. We assume that that reaction follows first-order chemical kinetics. So if we have this kind of arbitrary system like I put up here, I love box models. So anything I can put with a box and arrows, that's the way I like to begin this. Let's say we've got our methane here. I'm representing it by the molecule A, more abstractly. The H subscript represents the heavy isotope. The L abstractly represents the light isotope. We're going to see two different chemical reactions taking place here. One that involves the heavy isotope, one that involves the light isotope. Again, both of them are almost exactly the same, except they go at slightly different rates. More specifically, they have slightly different rate constants. And it's those differences in rate constants, here for a first order rate constant, we have these values of K, that ultimately lead to what we refer to as the isotope fractionation. Why there's a difference in abundance at some time later in reaction than there was at beginning, if we take that relative abundance of, let's say, C13 to C12. These two rate laws that we have here are normally integrated. Then we take the ratio of those two, and that ultimately leads out to this equation that we have here, which is referred to as the Rayleigh distillation equation. Now, I assume that a good portion of the people in the room are familiar with this delta notation. If you're not, all the delta notation really means is it's looked at as to me, the way I always look at it, is a percent deviation from a true value. You make a measurement, we always like to see how much in error we are. So we take our measured value minus our true value divided by true, and for our percent error, we multiply that by 100. However, here, our true value is simply a standard. We're making everything relative to a standard, and that's what we have right in here. And since our ratios here are so close, our values are so close to that of the standard, we want to blow that up. Instead of multiplying it by 100, we're multiplying it by 1,000. And that's all that we really have here. That's our delta notation. So again, we integrate these rate laws, we divide them, we simplify a little bit of the algebra, we come out with these equations. And these equations are very powerful for us because what it's telling us is if we make some measurement of, let's say, the methane isotopes at the beginning in that delta notation, we make it at some time later. If we know what this fractionation factor is, this ratio of that rate, those rate constants, then we can calculate F. And our F parameter here is our fraction of the sample that has been biodegraded. Glorious. All we need to do is make two isotope measurements. If we know what that fractionation factor is, we can determine right away what then our biodegradation factor is. So again, this is very sensitive though to that value of F. I'm sorry, that value of alpha, that fractionation factor. Because if this is what we have normally, one fractionation factor may ultimately give you this sort of distribution later. If we had a fractionation factor of 1, that would suggest that both then the rate constants are exactly the same. We're not really fractionating this at all. And biodegradation would lead to an equal amount of C13 and C12 in our final residual reactant. The farther we are from one, the more fractionation will occur. It's very, very sensitive to that fractionation factor. That's really our most fundamental parameter. The Rayleigh equations do the exact same thing. If we wanted to instead look at this from a product perspective instead of a reactant perspective, We can look at this with a product, say, containing the heavy isotopes and the light isotopes, make similar rate equations, make similar rate laws, make similar final isotope equations. And it really depends on what's easiest to measure in your system. In a methane sense, it's easiest to measure methane. Ultimately, it produces CO2, and there's so much CO2 in the world's oceans that that's a hard one to get good solid numbers on for this specific process. But again, none of this is new. This is all material that came out from what's referred to as Rayleigh distillation, or Lord Rayleigh's use of diffusion for the distillation of gases, which led to his discovery of argon and winning him the Nobel Prize in the early 1900s. But that same distillation process has been used to describe isotope kinetics and how molecules biogeochemically react for the last 50, 60 years or so. Here's the rub, here's the problem. Previous experiments doing laboratory cultures of microorganisms have shown that this fractionation factor changes with the stage of microbial growth. For example, this is an experiment. Both of these were two experiments that were almost the exact same as one another, but it was taking a laboratory culturing experiment of methane-producing organisms. And they have their growth media. It's rich in nutrients, got a lot of substrate in it. They plop their initial inoculant of cells in, and it grows up in response to these new conditions. And we see these growth curves with increased cells per milliliter as that goes on. This one here, this one's over here in the black curve of that growth curve from those early stages of growth to finally it reaches a new steady state or stationary stage. But what these experiments have shown is that the fractionation factor, if we're looking at methane production here, it's taking CO2 and reducing it to methane, that the fractionation factor for this process changes with the stage of microbial growth. And the early stages follows this growth curve. That's this line of experiments right here. We have values for that fractionation factor that are about 1.01. At that steady state value, the values are about 1.07. This is just another experiment corresponding to this one, displaying similar results. And in the other publication, we have similar types of profiles for both the fractionation factor at early stages of growth, going from about 1.01 to 1.06. In the Deepwater Horizon incident, we observe very similar things, where we see a bloom of microorganisms associated with this perturbation. In the early stages of the spill in May in 2010, even in some June samples, we have a system that's really dominated by organisms that were previously linked to the decomposition of oil molecules. Later on in September, in these oranges and reds, we're starting to see some evidence of organisms previously linked to the oxidation of methane now creeping in. So we see then the relative abundances change, suggesting there's a difference in the distribution that's occurring. Potentially we're seeing similar types of blooms and busts like we did in these culturing experiments. Instead of, though, having an enriched media which we add a few cells to, now we have a few cells which we're adding a heck of a lot more substrate to. And they're blooming up in response to that. So this now poses a serious problem, because it says to us that the fractionation factors change with the various stages of microbial growth. And that severely limits the use of isotopes for determining then the fraction of the released pool that's been biodegraded. Well, how big? Ultimately, we're interested in determining what the fraction is that's been biodegraded. If our fractionation factor changes from 1.01 to 1.06, they're both around 1. Are we talking about a 10% difference here in our final determination, 20% difference, or what? If we have, let's say, an early stage fractionation factor of about 1.005, somewhere around 1.01, let's not even go to the full extreme as that steady state of 1.07. Let's cut it in half and say 1.03. Values that we and others have measured in the Deepwater Horizon incident put the source isotope signature around -57 per mil for methane. What we measured while we were out in June of 2010 were some values that were in the around negative 48, 49, negative 50. Now, depending on what fractionation factor we have, if we're at the early stage of that microbial bloom as that's going up, if this is our fractionation factor, that isotopic change suggests that about 80 or 90% of it has been biodegraded. We come to the conclusion that basically it's all gone. However, if we have more of a stationary stage fractionation, and this is what's been measured previously outside of this spill for aerobic methane oxidation, this suggests that only about 25% of it has been biodegraded. We have two drastically different conclusions. One that basically says it's all gone, coast is clear. The other one that says the majority is remaining. We have black versus white. It's not a 10 or 20% difference. It's a yes versus no. So these changes in fractionation factor greatly limit the ability of stable isotopes to make this determination. And we can either throw our hands up and walk away and say, this is not going to work, we need to find some other proxy, or we can dive more into it. And that's where we really are and what I want to go over today. So I want to talk about and revisit those previous culturing experiments that some people had done in the laboratory, and how we can view those results maybe slightly differently than they were, as well as what the Deepwater Horizon taught us ultimately about how these fractionation factors change at the various stages of these microbial blooms. So first, let's look at these previous studies. There's two studies here, one that was done by Botts and one that was done by Penning. We see the different stages of microbial growth, the different stages of fractionation factors. Again, the black is the microbial growth curve. The open diamonds here are the fractionation factors changing. And if we ask ourselves how they actually measured this, how they determined it, they used a kind of an open system bioreactor where they have their growth media in here, and they're pumping it full of reactant, where they have their CO2 and their hydrogen, and the microorganisms here are then starting to convert that CO2 and that hydrogen into methane. Any CO2 that's not reacted flushes out, any methane that's produced flushes out that exhaust line. So in a sense, we've got an open system. Not in a sense, exactly, we have an open system. And that's different than the closed system for which the original Rayleigh equations are, again, that the authors used to calculate their fractionation factor. However, this open system can be viewed correctly as a closed system, just simply a closed system with an infinite amount of reactant. You can imagine if you had a massive closed system. We fill this entire room up with some reactant, we close the doors, we seal it off, we have some tiny little reaction that's occurring that's consuming only a very small part of it. We basically see no change in that reactant concentration. We would see no change in the reactant concentration, no change in the reactant isotopes, but a reaction would occur, it would be in a closed system. So we can look at this open system correctly as a closed system with an infinite and unchanging reactant concentration. So for my purposes, our original model here very much can approximate, let's say, an open system model. One where we have a rate of flow in, a rate of flow out, and a reaction that's occurring in this vessel, much like they have right in here. And these approximations, these are not approximations, these equations are interchangeable in the condition where we have steady state, where our inputs, that's our inflow here of CO2, equal our reaction term, what's reacted as well as what flows out of the system. And that seems to make sense on first glance. Whatever we're flowing in is either going to be reacted or it's going to be flushed out of the line. However, I don't believe that this is as intuitive of a representation as should be displayed. This is looking at the entire system. Really, the reaction is only occurring in this growth media. And so there's the potential then in that growth media for it to be not balanced, where the inputs do not balance what goes out of it. We look at this commonly as just being what's input, what's reacted, what's removed, but we don't really look at dissolution, because we're talking about a gas that's going to take some time to dissolve and come to a new equilibrium in the system. And it's that dissolution that can often cause these to not be in balance. If it's not in balance, that open system cannot be viewed as a closed system with an infinite reservoir. Let me explain. For example, we've got our open system here, and I describe it like this because I think it matches the picture very well, the schematic that the authors published. But really what's happening is we have more of that dissolution. I think this is more of an accurate representation of what's going on. In this sense, we can view it as, let's say we've got our media, and we prepared that media, and it's prepared in a room. And now we start pumping it full of 20% CO2, very high concentration of CO2. We're not going to have some go in and some come out at the same time. We're going to have a slow dissolution where the flux of material really is going from this headspace, if this is the headspace and this is the media, going from the headspace in with a reaction term. It's only when we get the concentration at saturation in the media where we have the inputs equal to the outputs via reaction and then exsolution. Really, what we're trying to say is, if we have this open system, we're flushing material in, and it's equal to this closed system with an infinite reservoir, the connection comes when there's absolutely no change in concentration. When the infinite reservoir is so large, that reaction does not change that concentration, does not change the isotopes. And really what we have to compare is how quick is the reaction rate versus how quickly is it dissolving. If the reaction is going really, really fast and dissolution is going really, really slow, we're going to see that concentration change as that reaction progresses until a steady state is balanced between inputs, losses, and the microbes finally reaching some steady state. If it's dissolving incredibly fast, then the reaction can't keep up. Whatever's reacted away will immediately dissolve more in, and our concentration will look as if it is infinite. So we need to look to see how quickly is this dissolving, and not just bulk, but each individual isotope. If it's dissolving in the span of seconds, then most likely this isn't a correct approximation. We're not going to see any concentration change, any isotope change as this reaction progresses. So we did just that. We took some sterile media, we took some sterile reaction vessels, and we saw how long does it take for this to dissolve in the isotopes to reach a new equilibrium. That's exactly what we have here. Again, this is not a solid line. These are discrete data points using the new technology of cavity ring down spectroscopy to measure the dissolved concentration of the C13 isotopes and how those change with time. And it doesn't really hit that new equilibrium until we've got this really dissolving in and flushing through for almost a 24-hour period. This is significantly slower than the methane production rates from these previous culturing experiments, but again, that's kind of a tough parameter to pull out from the data that is presented in those papers. So if then it's not balanced, if reaction is occurring faster than it's dissolving in, we're going to see a change in the concentration. We're going to see a change in the isotopes. We're not balanced with the input equaling the reactant. And there's some dissolution term that's now causing our system to not be in steady state until finally we hit that balance. It's not saying that it never will hit steady state. It's just saying most likely at the beginning of the experiment, before finally those microbes hit their steady state population, the dissolution and reaction finally balance each other out. Those points will hit steady state, but probably before that, there's a good chance that we're not. So we looked at that same model that we put together for here that was in steady state and said, let's relax that steady state condition and let it not have to be in steady state. If it's not in steady state, what if we say we assume it's in steady state? We actually calculate it as if it's in steady state like the authors do, but truly it's not in steady state. How much in error should we be? This is our parameter right here for how far we are from steady state. If we're in steady state, big F would have a value of 1. So in that condition, there's no error. We're in steady state, we're using the right equations, we've got the right fractionation factor. As we get a few percent away, our percent error then increases substantially. So I took then the previous data from these experiments and said, can I describe their data as having a constant fractionation factor if we assume at the beginning of these reactions it's not at steady state, and then finally it comes up and hits it? And the answer is yes. For each of these experiments, this is the data from that Botts paper, this is the data from that Penning paper. This is our parameter for how far out we are from steady state. A value of 1 indicates we are right at steady state. This is their culturing experiment time. We only have to be about 5, 6, 7% out of steady state. Steady state, again, is that balance between the sources and the sink rates. Only a few percent out do we need at those early stages of microbial growth. When those microbes finally hit their stationary stage, all the chemicals and the reactions balance out. We hit our steady state, but as long as we have that beginning period, that log phase growth being even a few percent out of steady state, we can model all of these as having a constant fractionation factor. That's huge for us. All of this variation in fractionation factor then goes away, and as long as we have a better understanding on how these things react, what kind of system we're in, steady state, non-steady state, open system, closed system, we can finally now use our measures of stable isotopes to get out the fraction that's been biodegraded. Then the Deepwater Horizon incident happened. And we tried to then put this a little bit to test. And in that sense, we needed to get a better understanding of how this reaction was progressing. How was the rate law changing, the rate constant changing? If the fractionation factor is a ratio of the rate constants for the light isotope to the heavy isotope, how are those rate constants changing and the like? So if we had a large methane perturbation here, how could we, number one, assess how the bulk chemical was going away with time? And the way that we approached that was to measure oxygen. If methane is just being dispersed, we're going to just see a concentration drop. We could measure the isotopes, but we don't know how it's fractionating potentially, if it's changing with the stage of microbial growth, if you believe what I said previously, or if it's not. So let's first see if we can get some sort of diagnostic to see how much methane has been biodegraded. And to do that, we looked at this oxygen profile. And we integrated these oxygen profiles to see how much methane was lost from each station. And we plotted these out over all of the stations we could get our hands on. These are not all the stations that we personally hit. There were roughly 1,300 profiles here. But one of the nice things about this flurry of activity around this event was that people took their fundamental parameters, of which dissolved oxygen was one, and made them publicly available so that we could get a much better, much faster understanding of what was going on, to help decision makers, to help workers, and the like. So we took all of these oxygen profiles, we integrated all of them, we plotted them, and we contoured that information out so we could see how that oxygen loss changed in space and in time. And that's exactly what we have here. We see time increasing, May, June 2010, and the contour out is the oxygen loss signature, and that's growing. This is just based on our data and the data plots that we do out. The total oxygen loss we have here is the accumulated dissolved oxygen anomaly. We see that growing with time. Certain time periods we have more stations, certain time periods we have less. You can see when the larger community gets more organized with certain sampling profiles, sampling strategies, until ultimately we get data limited as we get towards the fall of 2010. But if we plot that data up, this is the kind of profile that we have. We have our cumulative dissolved oxygen anomaly. And we have time on this axis, and we see our black points are our data points. We see this low at the beginning, starting to increase, and then level off, much like our microbial growth curves. And this is exactly what I think if we did a thought experiment and I asked everybody in the room to write how they think this profile would look, my guess is this is exactly what most people would write. At the beginning, the population is not very established. It takes them a little bit of time till they bloom up. And then their consumption rates of the hydrocarbons drastically increases. The oxygen loss goes concurrently until ultimately they eat up all of the substrate, they become limited in some way, and then the amount of oxygen loss levels off. Now, on the right-hand axis, I've translated this cumulative dissolved oxygen anomaly, this oxygen loss, to the amount of hydrocarbons that were actually there, that were respired, that were consumed. And that's simply based on a knowledge of what hydrocarbons were in this deep plume during this event. The black line here is what was measured as coming out of the well, what was released to the environment. This is a very hard graph to read, but there's many different hydrocarbons that are listed here on the horizontal axis: methane, ethane, propane, benzene, toluene, isobutane, N-butane, et cetera, et cetera. That's the black line. That's what was released. The red here are the relative abundances of the compounds that were found in those deep plumes that we investigated here. The black is what was detected in the surface slick. The blue is what was detected as volatilizing into the atmosphere. We really saw the mass go to 3 different places with relatively equal distributions in total weight that went to both places, to all 3. The deep plumes, the surface slick, and the atmosphere. So we can take what we know as being in those deep plumes in stoichiometric relationship with oxygen, and ultimately translate then this cumulative dissolved oxygen loss into a total mass of respired hydrocarbons. This gives us now our hydrocarbon mass, how much we've respired versus time. The first derivative of that should give us our rates. And that's what we have here. So we have mass versus time. How is that changing? Or dissolved oxygen loss, DO removal rate. And yes?
You had in the last graph, you had percent of leaking mass, but they don't add up to 100%. What's the, you said there were 3
Yes.
primary
Yeah,
reservoirs.
yeah.
What's the-
They don't add up. There's a few things in here. Number one, we don't have a full characterization of what was released from the well. We've got about 150 compounds, but we don't have all of them. And in terms of total mass, it comes out to characterizing about 50% of the mass. So that's one thing. For whatever's uncharacterized, we describe as a bulk hydrocarbon parameter. The other thing is that if we look at this with the appropriate uncertainties for these 3 locations where hydrocarbons ultimately ended up, our closure of the mass balance comes out to about 60 to 80%. So there's still a bit of an unknown on where some fraction of this mass ended up. We could debate for hours on where that is, or where that was. Excuse me. But yeah, I think that both of those parameters are really lying in there. When we take the derivative of this curve right here, we get these 3 curves. This just is the uncertainty in our fitting of that data. We see the slow rates at the beginning, it peaking at some time in the middle, it dropping off when it becomes substrate limited. And this black curve that's underneath it is the individual rates that we think, based on some modeling and some data, of the methane rates of oxidation. Again, slow at the beginning, peaking, and then decreasing down. Interestingly, this model agrees very, very close with the data in terms of timing of the peaks, as well as magnitude. It's spot on. But that model comes from an earlier paper that we had published, where really, thank you, Mary, we have 2 parameters. We break up that rate into both the methane concentration, and we see that dropping versus time. We have time on our horizontal axis. And the model predicts now the rate constant. It's not the oxidation rate, but it's the rate constant. And remember, for a first order reaction, the rate is simply the product of the concentration and the rate constant. So we take this concentration, we multiply it by that rate constant, and that's what we get right here. The dissolved oxygen loss are the circles that we see here, and they follow that same sort of profile that our data suggests right here, where it's slow at the beginning, increases, and then ultimately levels off. The reason it drops is we have a little bit of a mixing term in there as it dilutes and disperses. But this is what really kind of got me. We've got our rate constant. Our fractionation factor that we're talking about here is the ratio of the rate constants for the light isotope to the heavy isotope. And that, and what we're hoping is that that fractionation factor will be constant at all stages of a microbial bloom. However, we're seeing a drastic change in that rate constant for the bulk material that's reacting. The only way that fractionation factor would stay constant here is if both the light isotope and the heavy isotope rate constant were changing as dramatically but completely in concert with one another, so that they were all staying relative. And that's hard for me to swallow, to say that those two things change so beautifully together through such a large change in that fractionation factor, and that rate constant. This is the rate constant we have right here, going from values that were right around 0.0001 all the way up to values around 0.02. So that's a very, when we saw that large of a change in that rate constant, knowing the fractionation factor is the ratio of the rate constants for the light isotope to the heavy isotope, it made us wonder, now we probably did actually see a change in that fractionation factor with the stage of microbial growth, and these early papers were most likely correct. So, the experiments, the data we have so far describe this open system, and at this time period it was harder to measure those dissolved parameters since things like cavity ring down spectroscopy and other ways of measuring isotopes in a very high resolution manner were not available. But this is a very complex system nonetheless. Now we have a very complex, an even more complex system in the deep Gulf of Mexico. These stations spanned roughly 37,000 square miles. So let's simplify things. If both of these experiments are too complex and there's too many unknowns, and ultimately at the end of the day we can't tell if that fractionation factor is changing with the stage of microbial growth or not, let's simplify it. Let's do as an experiment in a closed system. And for that, this is one of my graduate students, having a little fun with the camera there. We did a mesocosm incubation last summer. Went out into the Gulf, we collected some deep water, and at this point we see no evidence of the hydrocarbons in it. And we pumped that deep water full of methane. The challenge here is to do it in a clean way. And anybody who's done these sorts of things knows how challenging that really is. If we do it in glass, it's great because it's impermeable to dissolved gases, and it's perfect for our experiments, especially because the Deepwater Horizon incident told us that this took place over a span of months. So it needs to be impermeable to dissolved gases. So glass is a great reservoir to do these sorts of incubations. However, the iron blanks from Pyrex glass are very hard to deal with, very high. Polypropylene plastics are commonly used for trace metal analyses, but those are permeable to dissolved gases. So you can see our sampling containers here are kind of a layered bag system with a polyprop inner liner, then an aluminum outer liner to keep the permeability down. Ultimately, we're pretty confident we've got low permeability and low blanks on this sort of thing. But we collected these samples of seawater from the deep Gulf, pumped them full of methane, developed a system that can measure the concentration and the isotopes of methane. We set it for every 8 hours over the course of a 2-month incubation. And we have about 8 or 9 experiments running here simultaneously, all controlled with an automated system. We bought the Picaro system, but we built our own front end to now enable us to sample each of these continually and measure these continually. This is the data from one of those experiments. We have the fraction biodegraded, the days of biodegradation, our C13 of the methane beginning at some values and getting heavier. And this is exactly what we would expect due to a biodegradation. The light isotope reacts faster than the heavy isotope. We see these delta values getting towards the less negative. That's exactly what should happen. But, so the data, the blue are our data points. The red is our fit to data. Here's the fit just as data points and days of biodegradation. The green is another fit to the data. Probably this is the easier one to look at. What this suggests, though, is that the fractionation factor is changing with time. Not good. We have, again, our Rayleigh model, first order chemical kinetic model for a closed system Fractionation factor here at the beginning, that's our red, is a fairly low value, like was predicted before with the lab culturing experiments, about 1.003. If we follow that the whole way out, our data does not match the curve at the later stages of that microbial growth in this mesocosm experiment. We have to increase the fractionation factor, much like was seen in those other laboratory culturing experiments, from 1.003 to 1.007, and that's that latter stage. And then that matches our data. So, again, we go back and forth on what actually might be happening here. When I look at now not the isotopes, though, and I look at the concentration data, for that first order kinetic model, it matches the data pretty good. It's hard to see, though. Beginning portion of this consumption, a lot of the data points are high of our line, of our fit. So we can match most of them, but just not the beginning. The beginning portion, the concentration seems to drop too aggressively. And again, if we look up here, we're matching the beginning portion of the isotopes with one model, but we have to change the fractionation factor to match the end. With only one model, we can do the beginning of the isotopes good, but not the end. We can do the end of the concentration good, but not the beginning. So this made me think, well, maybe there's something else going on here. Maybe those Rayleigh equations, this is clearly a closed system. We closed it off in our bag. There's nothing going in, nothing going out. But the only thing that's really else could be going on here is maybe this isn't a first order chemical reaction. Maybe we should model this as a second order chemical process. And that's exactly what we do here. Here's our concentration data. Again, we have the first order model, the red, hitting most of the data, not the beginning. Our second order model, though, hits that beginning drop, and it hits the latter ones. If we look at it for the isotopes, our fraction biodegraded, I think, is the best one here, instead of the days of biodegradation. But for our first order model, it hits the beginning data, not the end as well. Our second order model hits all the data beautifully. So that's really cool. We finally have, now whether this is actually a first order model, a second order model, it's hard to tell, especially in a system that's this complex in a mesocosm type of experiment. However, for these perturbation studies, what we have now, if this holds, is we have a way of describing the entire process with a constant fractionation factor. We have a model that is a second order model, same as the Rayleigh model in a closed system, it's just with second order chemical kinetics. Since we have that, now we can describe that as the fractionation factor being constant. Using that model, using a known fractionation factor, we can finally now calculate the fraction biodegraded. And if we relate this all back to some data that we've had from the spill, from stuff that was early on, stuff collected later, if we have a first order model with some fractionation factors that have been measured outside of this spill for this process, this indicates that only about 20% is biodegraded, the majority remains. Excuse me. For a first order model with some of the kind of the bad fits that we had toward the end data, this suggests that it's all gone. 90% is biodegraded. We're very happy. In reality, it looks like the best fit to the data is that second order model. If we follow that second order model, then, and this suggests that, excuse me, still a good portion, about 78, almost 80% of it has been biodegraded. So the majority of it, mostly of it, has been biodegraded. So in conclusion, we find that isotope fractionation appears to change with the stage of microbial growth. But this is using the traditional isotope equations, which is a closed system, first order kinetics. When we start to relax those conditions, those initial assumptions, we can start to describe this data as not changing with the stage of growth. And that's now having open systems that are not in steady state, that have second order kinetics. Our challenge now is to repeat some of these experiments, both the laboratory culturing and these mesocosm experiments, so that we have one unified theory. Right now we have a non-steady state condition with first order kinetics for that laboratory culturing experiment as the explanation. For our mesocosm experiments in the closed system, we have closed system second order kinetics. shouldn't matter what the system is. We can describe that as it is, but the kinetics have to be the same, meaning it should most likely either follow first or second or some other order. So the challenge for us now is to develop the theory. Can we describe this open system as a second order non-steady state isotopic fractionation? If we can, we need to then reproduce those experiments and see if it matches the theory and continue with those closed system experiments so that ultimately we can get that hopefully unified theory. If we can get those models so that then the fractionation factor indeed does not change with the stage of microbial growth, ultimately then all we need to do is put in two parameters. The isotopes we measure at the beginning of the process, the isotopes we measure at the end, and then hopefully we can pull out that fraction by integrating. Thank you.
Questions? Bruce?
I have a couple of related questions that are related to second order, which could mean different things. Perhaps it's monokinetics where your microbes are growing a little bit, which brings me back to the bigger question of the lag time in the kinetics. And those of us who've been on the oral exam committee that somebody told you we used your paper probably. You know, wondering, this phenomenal lag time in methane. But today we saw a lag in AOU from petroleum. So open-ended question. I guess first, when you say second order, what do you mean?
Yeah.
And then second, in terms of this lag in hydrocarbon degradation, it's fairly slow. We're talking months of buildup of biomass. What do you think is going on?
Good question. First question, second order. If we're describing our rate law like this, and for first order, I'm just looking at our reacting molecule, here being A. The exponent on that I'm saying is 1. For second order, I'm making that exponent a 2.
So that's meant, is there a conceptual model to go along with that N?
No, not that I know of. This is it's to me. To be honest, I approached this kind of as a chemistry 101 type of experiment. We all remember when we took intro chemistry and we see plots of data, we probably took some in the lab, of concentration versus time. And then we integrated the rate laws, we linearized the rate laws, and we saw which data fit that linear profile. And sometimes the rate law matched up the stoichiometry of the reaction, but not always. And so for this one, there was really no reason for me to choose a second order rate law, other than the data itself didn't seem to fit both the tail end of the isotopes and the front end of the concentration. It was an arbitrary decision.
But it could be a growth of microbial activity.
Of course, of course. So this, I don't want to state that this is what's going on. This is a true representation, but for this experiment, it seems like it did. The question for us is how universal is this, and can we match this up with maybe some more fundamental stuff? Now, the other quick question, and then was the lag stage.
Right.
And for certain things, we saw compounds going away very, very quickly. On other ones, not so much. For the bulk, there did seem to be a significant lag, and that just seemed to be the response time of the various organisms. The odd thing was that these are not done by one species. It's done by a whole host, with each with its own growth stage. So I wouldn't have expected it to maybe look as cleanly as it did for the oxygen loss profile, because you're going to have a bloom and a bust, and then a bloom and a bust, and then a bloom and a bust. But in reality, it kind of did. But that could very well be kind of the larger area that we're integrating over that helps to smooth things out.
Yeah, I mean, what's happening out in the Gulf is you have those blooms and busts periodically on different, time scales. And you could have water masses that come in and suddenly bring in some new group, and then they see the substrate, or another one that takes them away. So assume that it's one process like you can control in your mesocosm.
Correct.
Yes.
Correct.
And you have molecular biology data though, right, from some of those, I mean, Dave Valentine.
Yeah, we have some of that, but you know, the work that I'm largely doing here is with oxygen, and in fact, Dave, outside of the molecular biology work that he did a really nice model with Igor Mesic, also at Santa Barbara, a physical oceanographer, and tried to combine the three processes of biology, chemistry, and physics. And for our mesocosm experiments, everything's controlled, everything's still.
Right.
But in these locations, it's not. So if we have, let's say, a water mass that has a lot of oil in it, and it's a pristine water mass, there's going to be some bloom up of microbes. However, we have the physical process of mixing, and not all water masses simply flowed away from the wellhead after they were inoculated with their oil. There was a back and forth sloshing of that. Things were going towards the southwest, but they were kind of going in a back and forth sloshing motion. They'd go back and forth, back and forth, back and forth. So one of the things that they characterized, what seemed to be accurate, was this auto-inoculation process, where you had a water parcel, it was pumped with hydrocarbons, the microbes bloomed up, that took a little bit of time. Then this enhanced microbial water mass sloshed back over the wellhead, got a fresh batch of substrate, and then the oxygen dropped precipitously. So you have that extra factor in there that complicates things in the total oxygen loss picture. You can't just look at it as a straight growth curve. And what we're doing more is kind of a larger scale integration with respect to oxygen.
John Mack in the back.
Can you go back to your plot showing oxygen use and methane concentration and rate constant?
Yes. Took me a second just to try to figure out this slide so I can go there faster. Science papers. Yep. Oh, shoot.
So
hit it right on. That doesn't happen every day.
what did the delta C13 look like for that change in methane concentration? Was there a significant change?
Don't know. That unfortunately we don't have.
So how do you know that's not dilution right there?
That's not what?
Simple dilution.
Because of the oxygen signature.
No, because what if you have two water masses, one water mass is low in oxygen, whole, methane depleted, the other one isn't? How do you know that's just not dilution?
First of all, the oxygen, let me make sure I understand. And if I'm not understanding correctly, please correct me. The oxygen loss that we see is isolated to those distinct plumes. So we're not, when we subtract off how much oxygen is lost, we're not saying we have a representative DO profile that spans all of these. Instead, we're fitting a background to our DO profiles, and that SAG is really what we're concentrating on. We're integrating that SAG peak. So the depletion off the curve. So if there's a larger scale depletion that's occurring in the background Gulf of Mexico, say with an older water mass through global ocean circulation, that's not an oxygen loss that would come out in this model. That would be nothing. But we could say in these discrete layers, there's going to be an oxygen loss. And that oxygen loss could be attributed to the respiration of compounds that are not methane. Ethane went real fast, propane went real fast for ones that we specifically looked at, but a bunch of other hydrocarbons went fast as well that ultimately contribute to that oxygen loss. And the best that we can do in these sorts of situations when we're not prepared for it, when it's coming up on us with literally a week to prepare to get out on the water, and not to give myself any excuses, but this was not a scientific experiment that we planned a year and ahead to do. The best thing that we can do is follow the scientific method as closely as we can and ask ourselves, is the oxygen loss that we're observing coincident or in agreement with the amount of hydrocarbons that were there? We're seeing an oxygen loss that's so large, especially with the relative abundance of methane that's there, that we can't describe that oxygen loss without at least the bulk of methane being respired. We take methane out of the equation, we simply don't have the hydrocarbon mass to describe that oxygen loss.
no way, I mean, I'm looking at this plot, okay, and I see anti-correlation between methane concentration and PL. So, in spite of everything you're saying, if you go back and you look at the distribution of methane as a function of space that you have, there's
Yep.
a lot of heterogeneity. So, I don't see how you can say this is not due to its, or at least a good component of it, especially since I would have expected your delta C13 to show a significant correlation with your methane concentration that you just showed in your last graph. If you don't see that, that indicates that you're mixing.
We don't have that data. I can't say we don't see it. We simply don't have that data. The reason for that is, again, just due to the unexpected nature of this, as well as the fact that when we got back on the water, which was in the end of August, it was gone. It was not to be found. There was some residual, very small levels, but the concentrations are so small that they're beyond the analytical capabilities. We have data at the beginning of the spill, and when we were out in June, and as well as other groups have some. You know, again, if we were to do this in the idealized case, we would all organize a little bit, a lot better, so we hit this whole profile of growth as things progress. And you're exactly right. This can't be viewed as a system that's homogeneous. This is a very dynamic system with parcels of water that are most likely at different stages of degradation. But one of the experiments that we did do when we were out in June of 2010 was to see, can we get a little bit of spatial distribution on these isotopes? Because at that time period is when we had these high concentrations, easily can get enough sample for a quantitative measurement. And we did see that. We got a few nice cross sections of the plume. This is one of the cross sections that we have. As we get closer to the well, as we get farther from the well, and waters that we can guesstimate have different ages since their inoculation with the hydrocarbon, we do see a fractionation pattern. But again, getting that true age out of it, on how old that water has been since it crossed over and got inoculated, it's hard to do it. But if we compare this profile versus these stations, that distribution in methane data is a small line that covers literally about where I'm pointing my finger right here. So what we're trying to do here is really blanket the whole system, recognizing there's going to be a lot of complexities, and just trying to use the integrative power of area to get these parameters out.
I think we're going to stop the questions there, but please come to lunch and talk to Franchi.
Everyone can leave but Bob can ask.
Okay.
Okay. I mean, if you have to leave, go.
So one way to look at a second order system is as two coupled first order equations. And if you do that, then it suggests that there's some internal storage mechanism that decouples input from output. Is that a possibility in this case?
Never thought of it that way. But I think that could be a very, very interesting way of looking at it. And the two ways that we approached this problem, one was the laboratory culturing side, and the other way was more of the natural environmental experiment. I think we can kind of look at those two different ways. And the true way would be interesting to kind of petition them. The storage side, to me, dissolution of the different isotopes was surprisingly slow. I expected that to be a lot faster. So there almost seems to kind of be this lag, almost this storage term, just based on dissolution. So that could be potentially one of the things that's described in the laboratory side, if I'm thinking out loud. And that's what I'm doing right now.
That with nutrient-limited algae, for example,
Right.
nitrate-limited algae, there's a storage mechanism internal to the cell that does that decoupling.
The other thing that we recognized in our mesocosm experiments, as well as in our DO analyses, our DO analyses really only account for we look at the total amount of hydrocarbons that were in these deep plumes, we're getting to about 0.2 teragrams. But the total amount of hydrocarbons that were in those plumes was about a third higher. There's about a third, maybe 40% of the mass in those deep plumes that is not accounted for in this data. We don't believe that that is, although we can't say for sure, that that's not been decomposed or that is still in the water, that was deposited on the seafloor. We think that it is. And we base that just based on literature, where we have a non-complete conversion of a hydrocarbon to CO2, where it's stored as biomass. So we're really looking at this entire process of methane oxidation or hydrocarbon oxidation as going from a hydrocarbon the full way to CO2. But there is this kind of intermediary of bulk biomass, where you're building up that biomass population, and ultimately, as that population pluses, it's going to start to decompose and then go to CO2. So you have that almost that internal storage mechanism as well. And so that's in here. That could be another way. It could be nutrient, some sort of limitation that's also creating kind of this intermediary. There's a lot of complexities there. But I think that, to be honest, like I said, I never thought of it as two coupled first order reactions. And that might be a really interesting way of doing it, because then it starts to not just say what model fits our data, but we get to then have a better understanding of the processes that actually do.
Yeah, thank you. Thanks very much, John.